All right, we're going to go ahead and get started. I'm going to talk today about performance models, and specifically about a model that was actually developed by a former Berkeley grad student, Sam Williams, called the roofline model. And I just want to acknowledge that I am using a bunch of his slides. He gave this lecture last year, and by the way, if you want to see a lot more details on some of the things about how you run the various tools, I think the TAs will be talking about that in office hours, and you can also see that in the lecture notes. In addition to all these people that he acknowledged in his slides, because a lot of these people ran some of the experiments that are shown here, there's also some images that I took from another paper on measuring the roofline model by this group from ETH. So there's a lot of different people that we're stealing images from and so on. And this is the funding acknowledgments for him. Okay, so great quote from George Box, a famous statistician, which is, all models are wrong, but some are useful. Okay, and that's what we're going to talk about a lot in this class, is performance models specifically. And so the same thing is going to be true here. Some performance models, all the performance models that we talk about today will be wrong in some sense, and some of them will be useful. So the question is basically, what can you approximate and still get something useful out of it? And the tension whenever you're designing a performance models is how to make it simple enough that it actually gives you some insight into what the problem is, what the performance problem is, how you might optimize the code, for example, or how you might optimize the hardware, and accurate enough to actually give you meaningful results so that you're not optimizing the wrong thing. And of course, these kinds of questions come up all over the place, but they certainly come up in performance models, which is what we'll be talking about here. And I think maybe I may have mentioned this before, but there was some research done a number of years ago trying to build a very accurate model of the memory hierarchy on one of the, I believe it was on one of the IBM power processors, and it turned into many pages of equations. So that is a model that was, in order to get accuracy, in order to describe what was actually happening, you need to describe the associativity in the caches, you need to describe things like how prefetching works, all these different things, which turns into an enormously complex model. So if you want something very accurate, you end up with a very complex model. On the other hand, something like that may not be helpful in actually giving you insight into how do you optimize your code. So why do we use performance models? We want to understand the performance behavior of things. You will be asked in your final projects and in your homework assignments as well to sometimes give us some performance model information. You want to be able to explain. A lot of people will come in and say, here's my performance, and you just have no idea whether that's good or bad. And so you're trying to explain why the performance looks the way it does. Sometimes you're trying to compare different architectures. Why is one architecture faster than another? Why is one programming language faster than another? Another common problem that people run into in their final projects, and I know somebody asked about this in the first lecture, was, can you do your final project in Python? Well, problem with that, and a number of students ran into this, was it's very hard to get a handle on performance within Python. So Python is a great language for some high-level programming and putting things together, but if you really want to get at performance, you typically have to have some highly optimized libraries, at least, that Python is calling, or some pieces of code that you've written in another language that are being called by Python. So those are things that you might compare across each other. You might want to predict the performance on a future machine. So we do this a lot when we're build buying machines at a supercomputing center like NERSC, and all the vendors do that when they bid on a procurement. So we say something like, we want these 6 applications to run at a certain average performance on the machine, and so they look at those applications, they try to figure out how fast they'll go, they put in some kind of wiggle room because they know that they may not be able to predict accurately, but they put in a model of what they think their future network will look like and then what they think their future processors will look like, and make a prediction on how fast those applications will go. And it's very helpful in understanding if things are taking a radical change, as we're seeing right now in the architecture space, although it's much harder to make predictions when you move a code from one platform to a very different hardware architecture, because the characteristics of the code that you measure may not reflect how it's going to run on another machine. So for example, the number of loads and stores might be quite different on the current machine than it would be on some other machine that has, say, wide vector instructions. And so exactly how those will pay off, you can't necessarily tell by looking at the current code. You may need a new algorithm in order to take advantage of that architecture, and you can't just see it, make predictions from that. Identify the performance bottlenecks, probably one of the most important things you do with the performance models, and you'll see that today in the roofline model. Help give you some intuition and motivate the optimization. And very important, I always tell my graduate students, you need to understand when you're done optimizing the code, right? You need to understand that you're close enough to some optimal thing that you know you're not going to be able to exceed, that you should stop optimizing, because there's a tendency in, especially when you get into high performance computing, to say, oh, let me try something to see if I can make the code go better. First of all, that's not a very good idea if you don't have some intuition about why it's going to make the code go faster. But secondly, maybe you're actually very close to some inherent hardware limit on the machine. So far in this class, I've talked about memory hierarchies and single processors. Aiden talked about shared memory multiprocessors. There's our little cartoon of them. I wrote the word networking quotes. We don't really usually talk about these as a network, but there is some interconnection between the memory system and the processor on both the shared and distributed shared memory machines and on a single processor. So what are the critical performance issues that you're already seeing in homework 1 that we've talked about before? You've got slow memory, that is DRAM, for example, and fast memory, which was cache. And for each one of those, you may worry about the latency. What's the cost of getting some new address, some value that's at some new address in memory, the cost of, say, the first byte. If you're going to wait for that round trip to, say, issue the load, it goes all the way out through the cache, it goes out to the DRAM, and it comes back through the levels of cache. What is that latency? And what is the bandwidth? What is the rate in terms of the bytes per second that you can get memory data out of memory? And then at the processor level, there are, of course, all the parallelism things, which you are looking at right now in terms of optimizing the code as well, not just for memory hierarchy reasons, but also for parallelism on the processor. So the sort of hidden forms of parallelism in a sequential processor, such as instruction level parallelism, SIMD instructions, and I guess a question came up in one of the office hours I just want to point out, because maybe I wasn't very clear, that you do need to use intrinsics in order to get the SIMD instructions to work in GCC. The compiler will not automatically generate those instructions, so you'll need to write some code to do that in homework 1. And of course, having multiple processors. So what Aiden talked about last time, you would need to use OpenMP or some other kind of model. The compiler is not automatically going to generate parallelism for them, but all of that will affect the performance. So those are our kind of the way that we program these machines through reads and writes in both cases, but really with this extra level of memory hierarchy in here. We're going to start increasingly talking about distributed memory, and Jim Dummel will talk next week more at the application level, but he will be talking about how you divide problems up on a distributed memory machine and then think about the communication before them. I'll say a little bit more about that when we talk about performance modeling today, but I just want to give you a picture in your head of the fact that in addition to a single processor machine and a shared memory machine, there's also distributed memory machines, where the way to think about that is each processor has its own memory, and it communicates through some now real kind of network in order to get to the other processors, and that's what Cori looks like as a system. It also is what all the clusters and things like that look like, and I mislabeled those down below, but anyway, when I was cutting and pasting these, putting these slides together, I deleted the wrong column. But anyway, that right-hand column should say distributed memory machine. And we will talk about SIMD machines as well, I think the week after next, probably. So there's the version of it that we wanted, okay, with distributed memory. Okay, so the first thing we can talk about in terms of computational complexity, in terms of a performance model is computational complexity. So anybody who's taken an undergrad computer science algorithms course would be familiar with big O notation. I'm not going to go into a formal definition of that, but hopefully people are familiar with it in some kind of an algorithms or math course. But basically it's giving you a sort of approximate model of how an algorithm scales. And so what we're doing is we're assuming if we're just going to use computational complexity that the running time is correlated with the number of operations that you do, the number of arithmetic operations in particular that you do. So they say the floating point operations. And that the users are going to define their algorithms and their in terms of some smaller level kernels that are based on these that have a lot of these arithmetic operations in them, and that you can count them pretty easily inside of those in terms of some parameters such as the problem size, the dimension of the matrix, and how many floating point operations are there in the terms of the dimension of the matrix. And then we'll get the running time based on a formula that correlates with those parameters. So for example, this is a little bit small, but this is a DAXB, so we're just multiplying a vector x times a scalar alpha, adding it to another vector x, and then putting the result in a third vector y. And so common kernel that comes up in a lot of linear algebra operations, and this is an order n complexity, where n is the number of elements, so that's the amount of computation. There's a floating point multiply and a floating point add. So if you're going to put the constants in there, it would be 2n operations for the computational complexity. DGEM we talked about last time I lectured, so last week, order n cubed complexity, where n is the number of rows or the number of equations that you're solving for. And we will talk about a number of other algorithms that have other complexity, FFTs, conjugate gradient, multigrid, and body calculations, and you can see the formulas there. The point is just that they have different scaling behavior. So as the problem size grows, the scaling behavior, you would expect the performance of this code, just thinking about a sequential machine right now, that the cost of that computation is going to grow. Or even looking at a parallel machine, but thinking about a fixed amount of hardware, as you grow the problem size, then the cost is going to grow proportionally, we would say, with that formula. Okay, so some questions that come up that you can use this kind of computational complexity model for is what are the scaling constants? That is, as the thing grows, if we fit a model to one of these formulas, what is the constant that's out in front of it? And when does it depart from ideal scaling? We'll often see things that depart from ideal scaling. So let's look at a couple examples. Once again, going back to the matrix multiply and matrix vector multiply, but just to give you an idea, how do we turn this into a performance model for time? Well, we take the peak flop rate of the machine. So let's say on the Intel Haswell processor, both of these are on Cori, or the Intel KNL processor, there's the peak flop rates per core and the peak flop rates per node, because there's multiple cores on the node. So, and now we're not worrying about the details of what's inside of those processors, or how you get the performance out of them, or even how you're going to parallelize across those cores. We're just going to say, well, the peak performance of that node is over a teraflop in the first case, and whereas a single core is about 37 gigaflops, and similar numbers for the Knight's Landing, but a lot more cores. Each one of them is slower. There's just a lot more cores, so that's why they get to 3 teraflops. So we can then turn that into, and Jim will often use this notation gamma being the cost per floating point operation. And that is a throughput number that says if you've got a whole bunch of computation that you're doing, what's the kind of average cost of each one of those floating point operations when the processor is pipelined and you've got SIMD going, you've got instruction level parallelism, everything is happy. That's the only way you're going to get a peak gigaflop number like that. So the gamma is just 1 over the peak flops per second. And okay, the note on the bottom is because I'm often, and many other people use it without the /s, but flops can often mean either the number of operations that are being performed or the number of operations per second. And so you have to be a little bit careful when you're reading stuff to make sure you know which one is being referred to. So we do need the constants in here in the algorithmic costs. So you need to put the 2's in there and those are still a little bit approximate, but pretty close to what the computational cost is. So how good is this as a model? Well, on the left is data I showed last time. It's actually from that ETH paper looking at DGEM and DGEM-V, and this is on one of the fairly recent Intel processors. It's not Haswell, it's one of the earlier ones. But and so you can see that this is the running time for a given problem size, and so of course that difference in complexity means that matrix multiply is much slower than matrix vector multiply because it's doing a lot more work. And I built a little performance model in a spreadsheet that says, well, let's assume I'm doing 2 n-cube flops, and I did a little bit of munging to get the constant in front of it, and it looks pretty good, right? It looks like a similar kind of performance curve for the matrix multiply and the matrix vector multiply. I'm sorry, some of the fonts are so slow, but the top lines in both cases are matrix matrix, and the lower ones are matrix vector. But if I overlay them, I can see there's a bit of a problem, which is the matrix matrix multiply looks pretty good. That's, by the way, because I kind of fit the constants to it, but it's more importantly that because you're running at a completely different flop rate for a matrix matrix multiply than for a matrix vector multiply. And we can see this more clearly if we don't plot running time. It's very hard to see these kinds of things when you just plot running time plots, because oftentimes you're looking at some kind of polynomial growth in the running time, and so it's a little bit hard to see. We put it on a log scale, which can make it hard to see what's going on, although we'll use that again in the roofline model. But looking at some of the data I also talked about last week in matrix multiply, this was on the left a naive matrix multiply, a couple of different versions of matrix multiply, and one that was pretty highly optimized. That was a vector matrix multiply, not a smooth curve, right? This is now showing the performance also as a function of problem size, but the y-axis in both the left and right-hand side is the gigaflop rate. Actually, on the right-hand plot, they're using the number of flops per cycle, but it really is going to be the same shape curve as the number of flops per second, because the number of cycles is going to be the same. So just different normalization. So what you can see from this is now the number of floating point operations in DGEM per cycle is much higher than the number that's in matrix vector multiply. So matrix matrix is much higher, which we knew from talking about this last time. And so what is a better model for DGEM-V performance, that is matrix vector multiply, rather than the peak flops machine? So what's a machine parameter that would give us a better understanding of how matrix vector multiply is going to run on that machine, rather than the flops the number of floating point operations per cycle or per second on that hardware? Any ideas? Well, we're doing order n squared work on order n squared data. What do you think the limitation is going to be? Yes?
We have to look at the bottlenecks in terms of moving the data around.
That's right. You're going to look at the bottlenecks in terms of moving the data around, which really means the memory bandwidth. You're going to look at how much time does it take me to move, in the best case, just to move the matrix A into the fast memory. Ignoring all the other details, I at least have to move that whole matrix in. I have to move the vectors as well, but those are small by comparison. And so a much better model is probably going to be the data movement cost or the memory bandwidth. So we can look at the data movement complexity, and so if we assume that the runtime is correlated not with the number of floating point operations in the code, but the amount of data movement that's accessed, well, it's pretty easy to count the total size of the data that has to be accessed, which we might call the compulsory misses. That is the data that has to move, the amount of bandwidth that has to move between the slow memory and the fast memory. I can't do a matrix vector multiply without at least reading every matrix element once and every vector element once. Now this gets a little bit tricky, because there, of course, in practice is going to be much higher data movement between them for a problem like matrix matrix multiply, because I'm not going to be able to, if I have a matrix, if I have two matrices that are small enough that they all fit in the cache, including the result matrix, so 3 matrices, if I can fit them all in cache, then I could just move the two inputs, the A matrix and the B matrix, into my cache just once, do the multiply, write the C matrix into the cache, and then write it out once. And that would be the minimal amount. That would be sort of the compulsory misses that are going to be required. But in practice, in any of these algorithms, if the matrices are bigger than your cache, you're going to have to do more memory traffic than that. But this tells us for each of these different kernels what is the data movement complexity. So whereas the computational complexity, for example, for matrix multiply DGEM is n cubed, the data movement complexity is only n squared. And similarly for something like n body, which is you've got a set of particles and you want to compute all interactions between all pairs of particles. So just take all pairs of particles, there's n squared of those pairs of particles, and so there's n squared computation. So the computational complexity is order n squared, but the amount of data that inherently has to be moved is order n. And so the question then for this in this graph is, well, which one of these things is more expensive? Something that, well, certainly the growth rate in general is at least as high on the flop side, because what's the point of reading a data item in if you're not going to do at least one operation on it? So you'll see that the flops column is higher, but the more expensive operation is typically going to be the data column. And so a question of whether for a particular problem size, for a particular value of n, are you going to be limited by the floating point rate or the data rate, the moving data around. So this gets back into this issue of the machine balance or arithmetic intensity. So the data movement and the computational rates can be quite different on the machines. So that's why we use this notion of the peak double precision floating point operations relative to the peak bandwidth as the machine balance, which I talked about a little bit last time. And then we talk about the computational or arithmetic complexity, and I will say that a lot of other people use CI or computational intensity. Sam tends to use AI or arithmetic intensity, which is fine because most of these problems that we're talking about here are all arithmetic, but you'll see the terminology in both ways in the literature and things like that. So that is the number of flops performed divided by the amount of data that's actually moved, which is different than the top ratio, which is what the machine can do divided by what the machine can do in terms of bandwidth. So this has floating point computations. The ideal in an ideal world, you can just sort of divide the flops by the data column, and that tells you what your absolute best case computational intensity is going to be. And we'll see there's a lot of reasons why we won't actually get that. One of them is because, for example, you can't move the entire matrix for matrix multiply typically into your caches because they won't all fit. But that would give you at least one limit on the computational complexity. So problems that have a higher computational intensity are more likely to be limited by the floating point performance of the machines. Problems with lower computational intensity is going to be limited by the memory bandwidth. Now there are other things that can limit performance of the machine, of your machine, and this comes up in particular because of parallelism. And I talked a little bit about it when we talked about the things that come up, such as the read and write hazards that come up when you're trying to use, say, a SIMD unit. But it can also come up, and Aiden talked a little bit about this when he talked about multi-core and OpenMP shared memory parallelism. So one way of thinking about this is what is one reason that your code might not run at the maximum performance of the machine? Well, let's think about a multi-core machine just for simplicity. Let's say that it has 16 cores. Each one of those, let's say that they all have as much bandwidth as they want and all that kind of stuff. Well, there may be a problem that the algorithm that you want to run can't run on 16 processors throughout the entire computation. We talked about Amdahl's law, so the serial part of the code. But in general, what you'll see is that the computation, the parallelism, running time on a parallel machine is going to be limited by the depth of that computation, meaning the longest sequential path through that code. And one way of thinking about this is, imagine that I had an infinite number of processors, and imagine that the cost of memory is 0, and I'm just doing the computation. There's still going to be some depth in terms of the number of operations I have to perform, and that will give me some limit on the total amount of performance I'm going to get. And so for a particular algorithm, so for example, if you're adding up a sum of numbers that you will eventually have to add the last few numbers together, you can't entirely perform that in parallel. And so that will give you some depth, some logarithmic depth in doing the sum. And so there's also a bunch of overheads that come up in practice from these things. This gives you the depth for each one of these algorithms. So that's assuming, as I said, a kind of an infinite parallel machine. What is the longest path inside of that parallel algorithm? And that's just a function of the algorithm, not of the machine. So all of this whole table is just a function of the algorithm. The ones we've really talked about are DGEM-V, DGEM, and then the DAX-B I showed you earlier as well. So the DAXP can be performed, by the way, in constant time. If you have an n element vector, and assume that you have n processors, so and you have already given every one of them the constant that you're multiplying by, then they can independently multiply that constant and add it back to their vector element, and you can do in constant time then the DAXP operation. So whereas some of these others, most of them will have some other kind of depth, such as having to add a bunch of things together, which will give you some logarithmic complexity. Let me stop and just see if there are any questions here. Okay, so and in practice, by the way, you're not going to be running on ideal hardware where everything costs 0. You're going to be running on hardware where the cost of creating parallel threads will be non-trivial, and so these things will matter even more. When we start talking about distributed memory performance modeling, I just want to give you the idea that we're going to be worrying about sending messages between the processors. So for example, when you start worrying about that kind of cost, you can look at the overhead of sending a message. That is, how much time is the CPU, the processor, busy packing up the data into a message to perform a send or receive operation, and what is the time across the wire, the latency, if you will, what is the rate at which you can push messages into the network, and then what is kind of the size of the pipe in the middle of the network. And so these bandwidths and latencies are also going to be constrained by things like contention in the network. So you may be running an ideal setting. You've got the machine all to yourself, and you're measuring the bandwidth between a pair of processors that are sitting on this network, and everything looks really great. You're getting wonderful bandwidths, but in practice, for example, in the Cori system, there are a lot of other people running jobs. Those are also going to be sometimes sending data across the same network that you're using, and so you will see some performance anomalies in that. And so we're going to, when we get to the distributed memory, we will have to also look at the number of processors. So a lot of different things that I've just talked about can contribute to and be included in a performance model. And there's a lot of, even if you're looking at a pretty small piece of code, which we're referring to here as a kernel, so something like matrix multiply or matrix vector multiply. And so we can try to get some characteristics of them and try to figure out how to build a model. So this is a list of what I've sort of talked about. So the floating point, number of floating point operations, the amount of data moved into and out of cache, which we haven't really talked about measuring because it's very hard to measure that. The amount of data moved in and out of DRAM. If you've got, and in a couple of weeks, John Owens will be here talking about GPUs. The GPUs are going to kind of be glued on the side. You have to move data back and forth to the GPUs through something called the PCI bus, at least on a lot of those systems. I talked about the depth of these and then the MPI. The MPI is the message passing layer, so the different features that you may be worried about if you're trying to capture memory performance. So we can't think about all of these applications for all of these different terms for every application. So what we'll typically do is focus on some piece of the application that we're worried about. So for example, if we're just worried about the computational complexity, we'll just look at the number of floating point operations. And it is very important to include that, because if you don't worry about the computational complexity, you can have a really slow algorithm, such as you're trying to sort a bunch of numbers and you're using an order n squared algorithm. Even if you've got a really fast parallel machine, that's a terrible idea to use an algorithm that is much slower than the best known algorithm. So you do want to worry about that. There's models that look at things like the message passing cost. So there's one called log P that we'll talk about that'll look more at the networking layers, or and there's a difference between whether you, in terms of how they model the network, and which I won't go into details on, in terms of another variation called log GP. There's a model that looks at the GPU performance, which is called log CA, and that you can look at the references down at the bottom to read about each one of these. But what I'm going to focus on now is really looking at the roofline model. And the roofline model is going to take into account the number of floating point operations that you're doing. It can take into account the cache or the DRAM data movement. Typically, we'll look at one at a time, but we'll talk about a hierarchical way of looking at both of them. And the point of all of this is you need to use the right model for the right problem. And even going back to my original cartoon of what the different machines looked like, I dropped the caches from the distributed memory machine. Let me just go back to that one for a minute. Let's see if I can go back. And they did that because typically when we're programming at the level of distributed memory, we're not worried so much about the cost of moving data in and out of the caches. It's not to say the caches aren't there. The caches are still there. And so you may separately look at the model of how that processor performs in terms of getting memory in and out, data in and between memory and cache. But once we start looking at message passing, we typically then, and the cost of message passing, we won't try to put all the models together into one big, huge model. It just becomes too complicated. Okay, so moving forward, we'll look at, we're going to look at this roofline model. Oops, okay, I went too far. So, which is really partly based on the idea of throughput. And the fact that it's focused on throughput is related to something I talked a little bit about last week, which is that there's a lot of things that the processor is doing, various kinds of pipelining and things like that, which mean that you don't actually wait for the latency for things. In many cases, you wait for you're waiting for the throughput, or the rate at which operations, whether it's arithmetic operations or bytes, can be moved. So this is going to be a throughput-oriented model, and that's partly because in the last couple of decades, there's a whole bunch of techniques that have been put into the hardware in order to hide the latencies. Remember we talked about Little's law that says how much concurrency, so you're using some concurrency in order to, for example, have multiple reads or writes going between the processor and the memory, so that even though you do have a certain latency of getting to memory and back, kind of on the average case, what you're seeing is data coming back at the rate of the bandwidth, not coming back at the rate of in which it takes one load operation to go all the way out to DRAM and come back. Things like out-of-order execution, prefetching that can be done in the hardware or done in the software, and various kinds of thread-level parallelism that are going to be able to hide latency. And so for that reason, we're actually not even really going to distinguish right now in the roofline model much about the number of cores. So this model, it can be used on multi-core systems and on single processor systems. It is going to worry a lot about the computational intensity of the algorithm, and this is just sort of another graphic showing how the computational intensity varies. That's the same as that table I showed a little bit earlier across these different types of algorithms. But I will point out that even these little formulas here are just a model, because they're not taking into account, for example, that matrix multiply. You can't actually fit the whole matrix in there, so you can't reuse the matrix element n times if n is your matrix dimension. Okay, so let's see. I think that is buzzing. Okay, so let's look at the roofline model. And so it says it's a throughput-oriented model, and it's going to be useful in helping us understand the bottlenecks and to give us performance bounds on how fast things can go. So very useful. Probably the most useful thing about the roofline model is being able to tell you when you should stop optimizing, or when there's a lot of headroom that you maybe either don't understand your performance well enough in terms of what the bottleneck is, or there are things that you can do to improve it. And it's really independent of the details. As I said, even the number of the CPUs or multi-core or GPUs or TPUs, which are these tensor processing units that are in the Google system for doing deep learning and things like that. So you can use the model for all of these. Okay, so what does this model look like? Well, first of all, let's start with the DRAM, because we talked about how important the memory performance is going to be. We could always hope that we're going to get the floating point peak performance on the hardware, but for many, many applications, we're going to be limited by the bandwidth. Even in well-optimized code, we'll be limited by the bandwidth performance of the processor. So what we're going to do is assume that in kind of an ideal case for the processor, that the data all starts in the DRAM. So that means the caches in the processor are cold. So a cold cache means that we don't have any of the data accidentally sitting in there before, or intentionally even sitting in there before you before you start running the computation. There's some really interesting results in the ETH paper about cold versus warm caches and the roofline model, but which I won't talk about here. But we're going to assume that the DRAM, that the data all starts. So your matrices, for example, start in DRAM. Okay, and then we've got this bandwidth number, which is the bandwidth coming, and we're kind of ignoring the fact that there's some cache on there, but there's a place we're going to store the memory when we move it in there. And so what is the time is the maximum of the amount of time to do the flops. So that's the number of floating point operations divided by the peak gigaflop rate of the system, right? So that just gives you a seconds number. And so the other thing that can limit it, so the max of the number of bytes that you needed to move divided by the peak bandwidth. Okay, so in the best case scenario where we only move the data once, we can approximate the bytes by just those compulsory misses, that is the cost of moving the matrices in once and out once, and then we can get more refined about exactly how much data has to move. So we can refine both of those numbers. But we can rewrite this also as then the time per floating point operation if we're looking at sort of the rate at which you can do floating point operations, or the average cost of these as you amortize it over a large number of them, can just be rewritten by pulling out the common terms and getting 1 over the peak gigaflop rate is the maximum that you can get. That's the gamma that I talked about earlier, right? That's the cost per floating point operation, the number of seconds per floating point operation. And then at the bottom, what we have is the bytes per flop that we're performing times the peak gigabytes per second. So that is the arithmetic intensity times the, I can put in parentheses there. So that's the floating point operations divided by the bytes that I'm going to perform, divided by the bytes that I'm going to move, and then times the peak gigabyte per second rate. So you can think of that as how much of the bandwidth am I going to be, what percentage am I going to be utilizing, and that is given by the arithmetic intensity of the algorithm that you're running. Okay, so that's the ratio of the total flops performed divided by the total bytes moved. And so then we can look at this in multiple levels. So from the DRAM roofline perspective, it's the number of bytes that are moved from DRAM into the caches or the prefetching buffers. And it can be different than the number of loads and stores in the program. So I talked about this a little bit last time, and I know some of you are very familiar with it, but I talked about the way that what the actual code looks like on the machine has load and store instructions. Those are the memory operations. And the point is that some of those load instructions, for example, well, both of them, but let's talk about the load instructions, some of those are going to hit in the cache, and that will not cause memory traffic, and some of them will not hit in the cache. They'll miss in the cache and have to go out to DRAM in order to get the data. So the total bandwidth that you consume is not exactly the same. In fact, it can be quite different than the number of load and store instructions. You're hoping in homework 1 that you can make the number of load and stores be quite a bit higher than the amount of bandwidth so that you can get a better performance out of it. So what does this roofline actually look like? So we're going to plot it on a log scale, and I'll show you what the axes are. But the arithmetic intensity is going to be the x-axis, and the attainable floating point operations per second is going to be the y-axis. So that is the peak flops there that you can possibly get, and we can draw the peak flops line then as a horizontal line that will tell us we should never exceed that line. If we're exceeding the peak flops in the machine, it means we don't understand the peak flops in the machine, or we mismeasured our code or something like that. So the roof line is supposed to be the top of what you could possibly obtain, and things that don't have as much arithmetic intensity that the machine requires in terms of machine balance are going to run much lower than that peak flop rate. So the second thing, so there's our arithmetic intensity along the x-axis. That is measured in the number of floating point operations per byte. If you are using other kinds of operations, integer operations per byte, and whatever you want can be used there. Both of these, as I said, are log scales. And what that means is then we can also calculate the bandwidth as gigabytes per second will give us then on the hardware. So what is the hardware? This is just showing us a hardware profile, the peak flop number, and then the bandwidth number, the DRAM bandwidth number shows up as a diagonal line. And so you can start to see why it looks kind of like a house, maybe a piece of a roof line there. We've got that, maybe it would look more like a roof if we extended it out to the right a little bit further. But the basic point is that the rate at which your real algorithm for some other problem is going to run, for some real problem is going to run, should be underneath this roof line, right? Unless you've misunderstood something about the peak performance of the machine or something about your algorithm. You can't possibly send more data than the peak bandwidth that the hardware can send, and you can't possibly do more flops than the peak number of floating point operations in the hardware. Okay, and so we then will also divide the roofline plot into the memory-bound or bandwidth-bound piece, or the DRAM-bound piece on the left, and the compute-bound piece on the right. And once you have fixed on your problem that has a certain number of arithmetic operations, remember, don't run a naive algorithm that requires, say, order n squared flops when an order n log n1 will do. But if you've got a certain amount of work that you know you have to perform in order to do the computation, then you want that work to be as computationally intensive as possible. You want to minimize the memory bandwidth, which means you want to move things over to the right. So let's look at a specific example. A typical machine might have a balance of about 5 to 10 floating point operations per byte. Now that's actually quite a bit of work, quite a bit of flops that you have to do, because of course you don't do a floating point operation on a single byte, you do it on a double precision word, which would be 8 bytes. And so you have to, so you end up having to use something like 40 to 80 floating point operations per double word load or store that you're doing in order to get the compute capability of the system. So in order to run at that peak flop rate, your ratio has to be somewhere like around, say, 40 to 80 floating point operations per load or store. And this is an artifact of technology, and I often say that latency is speed of light. It's physics. You can't change latency, although in practice latency is limited by things other than the speed of light. You can hide it, and you hide it by doing all these various prefetching things. Bandwidth is primarily about money. And you can buy more bandwidth on a bigger machine, but it means more cables. That's a little bit of a maybe misstatement when you're talking about a chip because of the area issues, and I talked a little bit about this last time, but you're limited by the energy often that is used to get the data in and out of the chip. So there's just a limitation on the technology and the amount of money that you're going to put into bandwidth. And this ratio of, say, 40 to 1 in terms of the number of floating point operations per load or store is getting worse over time. It's unlikely to get better. There are some things that will make the amount of fast memory that you can get to a little bit better. So your kind of cache-like systems might be bigger, but that DRAM performance is not really getting any better. So let's look at a specific example like stream triad. So this is also looking at, so just multiplying a constant times a vector and then adding to the vector another vector and then putting the results. So there's just 2 floating point operations for every iteration of that loop. And you're transferring 24 bytes per iteration because you have to read x, you have to read y, the element of x, the element of y, and then you have to write the element of z. And so you've got 3 times 8 in terms of the number of bytes that you're moving, and so you've got an arithmetic intensity of 0.083, so nowhere close to the 40 that we want, right? So we're going to be way over here in the memory limited region of the roofline plot. So our arithmetic intensity now, flops per byte, is at 0.083, and we draw a line up and we can see that what we're running into is the memory bandwidth part of the plot, not the peak flops part of the plot. Okay. Let's see, a second example just to see how things changed a little bit. Next week, Jim will talk a lot about doing computations on meshes, and there's a common computation that comes up, which are stencils. It was one of the original 7 dwarfs of looking at structured grids, and this is just a little bit of code here that I won't try to read through, but it's just saying, well, say, a two-dimensional mesh, and I'm looking at the, or I guess this is a three-dimensional mesh, isn't it? Yeah, this is a three-dimensional mesh, and I'm going to look at an average of my nearest neighbors on that mesh, and so I end up with a 7-point stencil. I'm looking at the one above and below, to the left and the right, and front and back, times myself, which is the 7th one. And so I get those 7 values that I have to read and write, and I have to, and I'm doing 7 flops, and I'm doing 8 memory references, 1 for the load and 1 for the store of the thing in the middle, and then 1 load for each of the 6 things that are around you. So that's what I'm going to end up with this arithmetic intensity of 0.44, and I've got the cache in the middle. And I'm assuming that I'm only not, if I'm doing only the compulsory misses, I assume in the best case in running through this three-dimensional mesh that I only read anything in once. In practice, what will happen is if the mesh is too big, when you've gone around the corner, some of the things, say, above you and below you that are in the mesh will have fallen out of cache. So this is what a 7-point stencil looks like relative to Triad. So it's a higher computational intensity, but still bandwidth limited. But you can start to see now why this is helpful in terms of the giving us some sense of what kind of performance I would expect to get. I can't do any better, right? So, and you might say, well, but you told me that you're going to miss on other things in the cache, that you're going to have more than those compulsory misses coming back in the 7-point stencil, because some of them won't be in the cache the second time I need to access them, which is actually absolutely true. That means it's just going to be worse than this. So the best case is I can get a 7-point stencil that's at that point. If it's worse, if I'm doing more memory traffic, I'm going to have lower computational intensity. That'll push it over to the left. But this gives us a sense of whether we're kind of in the right ballpark. And it is important that it is using a log scale on both axes. We're not using this to fine-tune the last 10% of the code. We're using it to try to figure out, are we off by a factor of 2 in terms of utilizing our memory bandwidth or utilizing our floating point operations per second. And most importantly, are we bandwidth limited or are we flops limited, or are we right near the boundary between those? Okay. By popular demand, it's a little late, but we're going to take a 3-minute break so people can stand up and stretch. I will also take kind of one-on-one questions, but I'll repeat them back. If people need to leave, that's fine. If you need to take a little break outside, go ahead and do that. And but we will try to get back in 3 minutes, not 5 minutes, which I know was the vote, but there was an improvement on that. If I can turn this on. Okay. I think that was 3 minutes or so. We're going to go ahead and restart. So the next question that you might ask is, will the performance always lie on the roof line? Will they be at the bandwidth peak or at the floating point peak of the machine? And the answer, of course, is no. Oftentimes you will have things that will not run at either one of those peak limits of the machine. And it's kind of, just saying, can we achieve either one of those peaks? And what are some of the reasons that you're not going to be able to get to those peak numbers? One is that you can't get to the cache bandwidth because you don't have enough locality, you don't have enough reuse in the cache. You don't have enough vectorization, you don't have enough SIMD intrinsics, or you don't have enough pieces of the code that can even have SIMD intrinsics in them in order to get performance. Or you've got some load imbalance. So Aiden talked about this last time. I know there was a quiz question on it. If you've got your multiple cores, the only way you're going to get the peak floating point performance across all of those cores if all those cores are running all the time flat out, right? And so if you've got one core that runs out of work, then you're not going to run at that peak floating point rate of the machine. Okay, so now there's a lot of extensions of the roofline model that really get at memory hierarchy and also get at some of the more details of the architecture that are important in understanding why you might not be getting that maximum performance. And the first one is, so we'll build this hierarchical roofline that can look at, for example, what kind of memory bandwidth do you get in the L1 cache, the L2 cache, if you've got some other kind of DRAM, MC DRAM that's faster, but maybe not as large as your regular DRAM. So some kind of, so for example, on the Knight's Landing processor, which is the other processor that's on Cori, for homework 1 you're using the Haswell processors, although we do recommend after homework 1 that you start looking at the Knight's Landing processors because you'll probably get your jobs through more quickly on the KNLs. But you'll want to stick with 1 because you want to report results on something pretty consistently. And you have, and then you've got application locality issues within each level because each of these have different sizes. They are, this is pretty much of a strict hierarchy in this case. As I mentioned last time, sometimes you'll get non-hierarchical situations, but the L1 is smaller than the L2 is smaller than the MC DRAM, which is smaller than the full DRAM. And so they'll give you different bandwidth numbers in between them as well. So for example, you're going to get, each one of these will have a different number. So, and they're going to have different sizes as well in terms of the total amount of data that can be stored in them. So the machine balance then is going to be the gigaflop rate, which is the same at every level, divided by the L1 bandwidth, the L2 bandwidth, and so on. So the balance that you need is basically how much computation can you fit into the amount of data that you can get into that level of the memory hierarchies. And so this hierarchical roofline model is going to give us a ability to capture this. The arithmetic intensity also is going to be affected by whether or not you're talking about the L1 bandwidth, the L2 bandwidth, and so on. So here was our simple roofline model, right? It just had a peak flop rate and it had a peak bandwidth, or it had one bandwidth number, which was the DDR bandwidth, that was the DRAM number, and that was going all the way out to the DRAM. But you could imagine that if you have faster DRAM, that you can have a higher level of the bandwidth because you're getting to a smaller piece of memory, and so you're going to get a higher bandwidth, and so you have a chance of getting a higher peak flop rate. So you're kind of extending that peak region out to the left a little bit. What is the trick? The trick is you've got to make sure that you can fit all the data and the computation that you need in order to get that computational intensity number inside of that smaller level of the memory hierarchy. And similarly, sorry, I keep hitting the wrong way, you could get it into if you can get it into the L2, you might be able to get an even higher rate of memory of performance. And so if you can look at how you can optimize things. So the difference between these, the arithmetic intensity there will give us our DDR bound. That is the arithmetic intensity of the DDR is going to be less than the arithmetic intensity of the that's required in order to hit the MCDRAM arithmetic peak flops, or the attainable flops that you're going to get. So what does that say? That because the bandwidth of the MCDRAM is higher, right, you can get a, if you have a lower computational intensity, arithmetic intensity, it still may be enough to saturate that, that system, even though you're, at that lower computational intensity, and so you'll get a higher attainable performance number there, even for a lower arithmetic intensity. I said that all right. Okay. And so your DDR bottleneck is going to pull the performance though down below the MCDRAM, below this other level of performance. So so if you in practice you're going to have the performance is the minimum of the is going to be bounded by the minimum of these, and so you're going to, the best case performance that you can get is based on that that DDR. Sorry, the best case you can get is bounded by the MCDRAM if you're looking at that level of the memory hierarchy. But in practice, you'll see something often that's in between these, and that depends on how much of your traffic is going to DDR versus MCDRAM, or how much of your traffic is going to the level 2 cache versus going out to DRAM. And so this will give us a different bound for each of these. So the MCDRAM bottleneck is going to pull the performance below this level. Okay, so we get this hierarchical roofline that will tell us that for different levels of the memory hierarchy, we can actually get higher flops depending on what level of the memory, where that load and store is going to. Is it going only out, the loads and stores going out to the L2 cache, or are they going out to the MCDRAM, or are they going all the way out to DRAM? Now, the other thing that happens even on a machine with just a simple memory hierarchy, but it especially comes up usually on multi-core systems, is something called NUMA, which is non-uniform memory access. And what happens is you've got a kind of cartoon, a processor that looks sort of like the cartoon on the left that says some of the cores, say cores 0 through 15, are all nearby one DRAM because they're directly connected to that DRAM, and another set of cores, cores 16 through 31, are connected to another DRAM. And so if you have laid out your data in such a way that processor 0 is, CPU 0 is trying to get data from the other DRAM, and CPU 1 is trying to get it from CPU 0's kind of nearby DRAM, they can all get to both DRAM, right? So they can access them, but the cost of going across to the other side is going to be much higher than the cost of going to within your own DRAM bank. You'll get lower bandwidth going across than within. Yes?
Is this something that you generally have to account for as a programmer, or the operating system take care of allocating memory such that it's efficient?
Right, very good question. The question is this something that you as a programmer have to worry about, or is this something that, say, the operating system will that will automatically manage for you? In this particular case, it would really be the hardware that would probably be managing it for you, but it does have to do with where your arrays and things are living in memory. You do have to optimize it for it if you're trying to get the maximum performance out of your machine. You'll have to worry about it in software. What does that mean? It means you want to, for example, allocate a chunk of memory where you kind of know that memory is all contiguous and how it's going to be striped. You can also pin memory and things like that using intrinsics to try to get the memory allocated. So one of the things is have the CPUs do their own memory allocation. Don't have CPU 0 do all the memory allocation and then hand a pointer to it to the other CPUs. That is very likely to give you bad crosstalk in terms of accessing the memory. So you do have to worry about it a little bit. Yeah. Okay, so that will give you something that runs slower than the DDR did, right? So you had the DRAM bandwidth, but now instead of getting some faster memory that was giving us higher bandwidth, we're actually getting some lower bandwidth if we've not optimized for NUMA and we've got a NUMA problem in the code. Now maybe accidentally or whatever, your code was written in a way that it'll just be very happy in terms of the bandwidth, and it will be using the different banks of the different DRAM parts separately. But in practice, you may need to, you'll run at a slower bandwidth rate if your program is accessing data across the different DRAMs. Now, a lot of times this will happen, and specifically on the Cori system, there's two sockets. So without going into details, just think of it as kind of there's two processors, but there's some wires going between them that allow you to access the memory between them. And so what happens in a lot of parallel programs is people will run one message passing process on each socket. So you kind of think of them as two separate processors, even though physically they can directly share memory. So that's the other way that you worry about it in software, is if you have a message passing program, MPI, which we'll talk about in a couple of weeks, and you rather than having a piece of parallel code sitting on every node, you'll have a piece of parallel code sitting on every processor. And then you'll use OpenMP only within one socket, not OpenMP across the whole node. Good question. Okay, so let's see. So let's talk about how the other things that can go wrong and can limit your performance. So that's some of the things that affect the slope of the roofline model. There are other things that affect the roof, the flat part of the roof of the roofline model. And so far what we've assumed is just that you can attain the peak flop rate, assuming you've got the right locality. So if you've got enough computational intensity, you're going to be sitting there over under the flat part of the roof, and you should be able to get you should be able to get something like the arithmetic peak. So this is now saying, forget about the question of the loads and stores. Let's just look at the mix of arithmetic instructions and see whether we have any problems there. And so what are the things that I talked about briefly, and that you're certainly going to be thinking about, I think, in the homework assignment, is vectorizing the loops, trying to use those SIMD instructions that are actually going to do loads and stores on chunks of memory rather than just doing individual loads and stores on an individual word in a matrix. So you want to be able to load and store those and then do vector operations on them, so multiplies and adds on those little vectors. You want to use the special instructions like the fuse, multiply, add that I talked about, right? So the hardware, because of the popularity of doing a multiply followed by an add on the same values, you often have this fuse, multiply, add instruction that's inside the instruction set, and you want to use those to get the maximum. That's the only way you can get the peak performance, is if you're using those. And you want to ensure that if you look at your whole mix of instructions, which might include branches and logical operations and other kinds of things in addition to floating point operations, you want to try to get your floating point operations to be the main thing you're doing. So what would that mean? That would mean getting rid of some of the branches in your code. One of the optimizations that you might want to do is unroll your inner loop inside of your matrix multiply. So write a little 3x3 matrix multiply. You'll have to decide what's the right size. And that could be completely unrolled straight line code, because it's doing exactly the same thing independent of what the values inside of those little 3x3 matrices are. And that way you're getting the things that are saying, am I at the end of the loop or not, out of the middle of the code, and just having a series of floating point instructions. And you want to be able to use all the cores and all the sockets. Okay, without doing all of that, yes, question?
I heard the hardware rank predictors are pretty solid recently, like nowadays. How do we know if it is doing its job, or if like branch prediction is a bottleneck of our code?
Right, so the question was, hardware branch predictors have gotten better over time. There's little algorithms in there. So what's a hardware branch predictor? Hardware branch predictor is saying inside of, if you've got, say, a loop or you've got a conditional, that the hardware can do a pretty good job of guessing, is it going to go on the then branch or the else branch, or is it going to go around the loop again, or is it going to fall out of the loop? Now, the problem is, what is it doing in that case? Well, it's looking for the average case. And if you've got a little tiny matrix multiply that's a little 2x2 matrix, the branch predictor might say, oh, I'm going to predict that you're going to go through another iteration of this loop, which it's going to do for the first 4 times or whatever through the loop, but it may not be able to predict that, and that's one reason why you might want to unroll the code, is because the branch predictor, it can't guess which is the time it's going to run off the edge. I mean, it may be. I mean, it depends on how much logic is in the branch predictor, but that's where you may want to run into, you may have to do software optimizations. How do you know that? Well, you don't know exactly what the hardware branch predictor is doing. What you will see is you're not getting the peak flop rate. And so it'll be one of the things that you'll try to do to try to optimize the code, is say, can I, do I have some branches in the middle of my code? I don't want branchy code in the middle of my, if I've got even if I've got a big, huge million line of application, somewhere down at the bottom someplace I'm doing little tiny bits of computational work. I want to make sure there's as few branches in there as possible. And as a result, people sometimes do things like make tables of values that you're not saying, oh, if the value is less than than this, use A, and if it's greater than that, use B. Instead, you just write it out in such a way that you've got a table lookup or something. Very good question. Okay, you also need to have full SIMDization. I talked before about you got to use intrinsic in order to get the SIMDization. You also have to have a code that you can actually SIMDize. For example, the Knight's Landing processor that you'll be looking at later is 512 bits, the vector lengths, and so 8 64-bit words, and the GPUs often have 32 thread warps. So John will talk more about what thread warps are, but basically this is some kind of data parallelism. Data parallelism we'll also talk about more in general, but it says I'm going to do the same thing on a whole bunch of data values. And in the case of SIMD, it's not that many data values. It's something like eight words. I'm going to do the same thing at 8 words or maybe 16 words. And so you only are going to see that peak flop rate if you're running fully vectorized code, because that's the only way the hardware will typically see that maximum performance. So looking at it another way, what do the marketing people do at the hardware companies is they say, what is the best possible thing that will run in this machine? Let me take that number and advertise it as the peak flop rate of the machine. Guaranteed not to exceed number, that's what the flop rate is. And so in practice, if you don't have vectorization everywhere in your code, even if there's like bits of your matrix where it's no longer 8 words long because the matrix size is such that you've fallen off the end of that, then you might not be running at that full vectorization level. And so in practice, you're going to have a mixture of vector and non-vectorized code. And so you'll run, and the roofline can capture that by having different lines that tell you what the peak performance is depending on whether you've got vectorization. And in practice, you might be running somewhere in the middle where you, so having nothing to do with memory accesses, or even if you are, that it may look like your memory bandwidth limited, but in fact the problem may be that you don't have enough vectorization. So you're actually not even running at the memory bandwidth limit, right? So you are in the memory bandwidth limited part of the curve, and so of the roof line, but you're not actually seeing the maximum memory bandwidth, and that's because you instead have this problem with the too many instructions that are not vector instructions. And so there's kind of an implicit ceiling then for whatever application whatever instruction mix you have that it gives you the top of that for partial vectorization. So for example, here's some, So for example, if you've got if only half of your instructions are vector arithmetic, floating point instructions are vector, you're going to be at half of the peak of that in terms of the mixture of instructions. Okay, so what are the other things that is happening? Well, beyond the fuse, multiply, add, that's just one example of more complicated instructions that are going into some of these processors. This is attributed in part to the end of Moore's law, and it was if you follow the history of computer architecture at Berkeley, we really pushed for the RISC architectures, that is reduced instruction set architectures, so a small number of instructions in the entire architecture set that you write your software in at the lowest level. But what's happening is, as people can't get the processors to go faster with those, they're making up more complicated instructions that they can then, for example, pipeline inside of the hardware and get those more complex instructions to run at a rate of 1 per cycle, even though they're doing more than a single arithmetic operation. So FMA, fuse, multiply, add, is 1, but there's a 4 FMA thing, which is where it's being done in a little vector. The tensor core also has even other operations like that. And so these are becoming increasingly popular also for things like machine learning applications, where you have an instruction mix that you might be able to specially optimize for. And now it's going to be a weighted, the performance that you get, the maximum peak on that roofline is going to be a weighted average of the scalar, vector, FMA, and so on operations. Okay. Let's see, the other thing you do have to think about at the hardware level is superscalar instructions. So if you're reading documentation on, for example, what the Haswell processor does or what the Knight's Landing processor does, it's actually issuing multiple instructions on a given cycle. And I didn't really talk about this in detail when I sort of said instruction level parallelism. We talked a little bit about pipelining, but the processor can actually issue multiple instructions. And so it may be that you can get at the hardware hardware level you're getting some parallelism there. That's going to affect your floating point rate. Why do you have to worry about that? Is because if you've got hazards in between your instructions, that is, you've got a little bit of code where the first multiply is dependent on the second multiply is dependent on the third multiply, that is, that they're using the, X is used in each one of those on the left or right hand side of each one of those statements, then the hardware is going to detect that it can't run those different multiplies in parallel and won't issue 4 instructions for those 4 statements that are in the middle of the code. So you may want to try to write your code in such a way that, that you've got independent operations that could be parallelized so that the hardware can take advantage of that. But it's also the case that the number of instructions that it's issuing may be different than the number of floating point units that it has. So for example, it may have only 2 floating point units, and even though it's got 4 instructions per cycle. And the ratio of these 2 rates, that is the number of instructions issued divided by the number of the floating point operations, is going to tell you what kind of instruction mix you need to have in order to keep the floating point units saturated. So that's the name of the game in the roofline model, is to fully saturate your floating point units. And if you've got an instruction mix which has got more than half of your instructions are non-floating point instructions, then you are going to not be able to keep that saturated. So on the Haswell processor, it's a 4-issue superscalar. It requires only, and it has only 2 floating point data paths. So think of that as 2 little, multiply, add, et cetera units that it can do the floating point instructions in parallel with each other. So on a single cycle, as the clock is ticking, it can issue 4 instructions, but only 2 of those can be floating point instructions or can be retired at that rate. And so it requires that half of the instructions have to be floating point instructions. And the problem is typically that you don't have that many floating point instructions. You've got less than half of it. And so if you've got at least half floating point instructions, you'll be at the peak rate. And otherwise, if you've got, say, you'll be at, if you've got only 25% floating, you'll be floating point instructions, and you'll be, and the others are, say, integer instructions, and you're going to be a factor of 2 down, and so on. On the Knight's Landing processor, it's a little bit different. It's a 2-way superscalar with 2 floating point units, and so that requires that 100% of the instructions have to be floating point in order to get peak performance. What does that mean in practice? It's very unlikely you will ever write an application that runs at 100% of the peak performance on the Knight's Landing processor. Okay, so codes that would normally have been memory bound and been over under this DRAM DDR bandwidth bound, so you would expect to see that they're hitting the peak bandwidth, are actually instead limited by something like the floating point mix of the instructions. So they can actually be floating point arithmetical intensity, or arithmetic operations bound. And so that's why you have the multiple layers of the roofline, so that you can see that there might be some other reason that you're not hitting your peak. Okay, so you can also extend the roofline model to model cache effects. And I think that I will, so there's these locality walls that say that how much data do I have to read, and that gives me a certain amount of computational intensity. So that might say for matrix multiply, I'm all the way over here on the right, I should be peak floating point limited. But in fact, maybe that you need to also allocate in your caches, you might run at a lower arithmetic intensity. For example, the write operations you're doing that may not seem like they're actually taking up memory bandwidth are going to be allocating memory in order for those writes to go back to the DRAM eventually. And the cache capacity misses also are, that's probably the most important thing, which is that you can't fit everything into cache. So as I said before, if you're running dense matrix multiply, you can't fit all of the matrices in cache, and the capacity misses are the thing you mostly have to worry about, which says that I read a piece of A and a piece of B, and I do some of the multiply on them, and but when I get to some of the elements of the next elements of A and B, I may want to reuse some of those values, but they're no longer in the cache. And so that will give me a line that is further to the left, and so that can make my roofline even smaller. And so something that used to be, that seems like it should be compute bound, could be memory bound because, for example, my cache is too small, right? So we haven't really talked about cache size so much, but if the cache is too small, then you don't have enough storage inside of your cache that you can hit the peak flop rate, and so then you'll be memory bound as well. Okay, so a little bit about why the roofline model is useful. So imagine that you've got some set of loop nests in your code, whether it's matrix multiply or maybe something more complicated that you haven't seen before, and you might be looking at a number of different kernels or applications. You can compare across the different applications to figure out what your floating point rate. You could try to just say, well, what's the flop rate of all of these? And this is very common in the literature, is to say this application is running at a certain flop rate, another application is running at another flop rate, but it doesn't really tell you why they are what they are. If you sort those applications based on their arithmetic intensity, you tend to see a pattern that will look sort of like the roofline. Okay, so for example, we'll see that maybe not all of them are running at the roofline, but if we've got some of them, so maybe that's a DAXP over there on the left, or matrix vector multiply, and then somewhere in there, and then we've got something like a matrix multiply on the right. Sparse matrix multiply, matrix vector will also be over on the left. Maybe the stencil thing is one of the ones that's a little bit higher up on the roofline. So sorting them can be a really useful way of getting some sense of why you're getting one performance on one application and a different kind of performance on another application. Kernels that are near the roofline are using the computational resources very effectively. If they have a low performance, but they're using the machine well, then what does that tell you? That says, well, can you come up with a way of doing less memory traffic, that is moving your computational intensity to the right, but because you're already using the things well. But the kernels that have high performance but are making poor use of the machine then are going to be further away from that peak. So it tells you how well you're using the machine given the way you've kind of organized the data movement in the code. And you can do a new optimization kind of for the roofline every time you change the code to make sure that your code you haven't had performance degradation in the code. And you can also do something fairly interesting, which is to look at how you progress over time in terms of relative to the roofline. So maybe you start out here, you're at sort of the version 1, where you're not even close to the roofline, but you're under the memory bandwidth limited piece of it. Now version 2, you've both moved to the right, so you've somehow reduced your amount of memory traffic for the same amount of computation that you're going to do, but you've also optimized somehow let's say you've added prefetching or something, which allows you to get closer to the peak bandwidth of the hardware. There's version 3 where you get even closer. Maybe you can think of new optimizations based on that. And now maybe you come up with a completely new idea. I hadn't actually blocked the code for matrix multiply, or maybe there's another level of the memory hierarchy, something that I haven't taken advantage of, so I can increase my computational intensity by reducing the number of loads and stores and moving significantly to the right, which automatically might move me up. So there's, in comparison, a very common thing to do to compare across applications is to look at the running time, sorry, the rate that you're getting, the gigaflop rate that you're getting on these different applications as you add parallelism. So this is might be a weak scaling plot. So we might have different size problems that we're running on different number of processes, but we often look at that, the gigaflop rate that we're getting across the different sizes. So there's a really interesting thing, though, you can also do, which is to look at how things change as you vary the computational intensity, but also change as you change something like the matrix dimension or the problem size. And so these plots are actually looking at different problem sizes, and when I first saw them, it was very confusing about why do they go to the left? Well, what has happened is you're increasing your computational intensity maybe as you make the problem size larger, but then it gets too large and it falls out of some level of memory hierarchy, and you actually get worse computational intensity than you did for the problem size before, because it used to all fit in some level of the memory hierarchy. So the ETH paper also has a whole bunch of these, although these trajectory plots were actually developed by somebody here at Lawrence Berkeley Lab, I think Khaled Abraham, and they give you interesting performance plots as well. They can help you really think about how to do the optimization. So, is there any way that I can come up with FMAs? Are there things that I can do to vectorize the code so that I can get the code up higher, closer to the peak flop rate? Things like that will move you much closer and give you some intuition about if you understand what the roof line looks like. So remember, the roof line itself is just fixed for a given machine. But these different layers might tell you of the roof might say, for a particular problem, if I'm not doing matrix multiply, if I don't have an equal number of multiplies and adds, then I'm guaranteed to be, let's say I'm only doing additions inside of my code, I'm not going to be running at the FMA level. And there's memory bandwidth optimizations if you're sitting there over underneath the memory bandwidth peak that you might be able to do, such as NUMA optimizations. So a little bit of practical ideas about how do you build the roof line. And I won't go into this in detail, but you can meet with the GSIs during office hours, and they will be happy to point you to some of the tools. But there's a bunch of documentation on the NERSC website, so you may be able to use these just by looking at the tutorials and things that are online. So over the years, there are a number of different tools that have been built for developing these roof line pictures. And I think at this point, what are the things that you need? Well, you need the theoretical performance of the machine. If you can find somebody who's already measured that, for example, the Haswell processor or the Knight's Landing processor, there's quite a bit of documentation on the roof line for the KNL system at NERSC. It was a little harder to find the Haswell one, although there is one that's online as well. And you can try to use these from the stated peak, which is on, say, the NERSC website or the vendor website for the processors, but you need to take those with a big grain of salt because you may never be able to write an application that achieves them. So let me just not go through all of these examples because I want to also point you to one of the tools here. Counting the floating point operations and the floating point intensity is also quite difficult, and you can try to do it manually, but it's very tedious. You can try to use performance counters, which gives you more accurate numbers. So there's hardware down there that will try to count things. It turns out some of the counters on the Haswell are actually broken, so it's not such a great model for that particular one. And you can try to instrument the binaries in the code, but those are going to be by counting the number of load and store instructions, but it still doesn't really tell you what's happening in the cache performance. And how do you measure data movement? Well, that's even harder, but also, I guess I was talking about cache performance there. So you need a real cache simulator to talk about the hardware performance. So initially, this was done manually. In Sam's thesis, he used lots of different techniques on different machines to measure the peak performance of things. There's tools like Intel's vTune, but that got replaced by something called Liquid. And there's just links on these slides. And there's also, by the way, more details in the slides that will go online if you want to see more details of how to run these different tools and things like that. And the most recent tool is something called the Intel Advisor. So that's really, and I will just end there by saying, there is some help to try to build these. I do think it's a very useful way to think about your code, not just for homework 1, but all the way up through the project, is to think about, for at least on a single node, and we'll talk about other performance models for the network, but what is the expected performance? How close are you getting to the optimal, and things like that. Questions? Okay, thanks very much. We'll see you next time.